Experiments on the identity of electric waves and light. Hertz apparatus for shorter electric waves. After Hertz had succeeded in proving that the action of an electric oscillation spreads out as a wave into space, he planned experiments with the object of concentrating this action and making it perceptible to greater distances by putting the oscillator in the focal line of a large concave cylindrical mirror. In order to avoid the disproportion between the length of the waves and the dimensions he was able to give to the mirror, Hertz made the oscillator smaller, so that the length of the waves was less than 1/10 of those first discovered. The form of oscillator used in these experiments is shown in Figure 28. The two halves of the oscillator were cylindrical bodies 3 centimeters in diameter, terminating in spheres 4 centimeters in diameter. The total length of the oscillator was 26 centimeters, and the spark gap was usually about 3 millimeters. For a receiving circuit, the circle of wire used in the previous experiments was replaced by a linear resonator consisting of 2 straight pieces of wire, each 50 centimeters long and 1.5 millimeters in diameter, adjusted in a straight line so that their near ends were 5 centimeters apart. From these ends, 2 wires, 15 centimeters long and 1 millimeter in diameter, were carried away parallel to each other to a micrometer spark gap, similar to that used for indicating the waves in the previous experiments. The method of mounting the oscillator and resonator in the focal line of the cylindrical mirrors is shown in Figure 29. The reflecting surface of the cylindrical mirrors was of thin sheet metal. The dimensions of the reflectors are shown in the diagram. With these reflectors about the oscillator and the resonator, Hertz was able to get indications of waves up to a distance of 20 meters. The length of the wave, measured by the method of the last experiment, was 66 centimeters, and the period of oscillation, assuming that the waves travel with the velocity of light, was 2.2 thousandths of a millionth of a second. With this wavelength, Hertz succeeded in carrying out many of the elementary experiments that are commonly performed with light. Rays and shadows. With the electric waves, as with light and radiant heat, shadows may be cast by objects opaque to the waves. Hertz found that a metallic screen interposed between the oscillator and the receiver in the position A of Figure 30 stopped the sparking of the resonator completely, while the 2 screens in the position B and B' did not materially diminish the sparks at the resonator. If, however, the opening between B and B' was made narrower, the sparks became weaker and disappeared when the opening was reduced below a half meter. In experiments of this kind, although the dimensions of the screens are measured in meters, these screens are yet not large in comparison with the wavelength of the waves, and the phenomena of diffraction are very marked, so that there is no sharp geometrical limit either to the rays or to the shadows. Polarization. Hertz showed that the electric waves produced by his linear oscillator are polarized waves. One way employed by him for showing this was to start with the focal lines of the 2 reflectors parallel, as in Figure 29, so that there is lively sparking at the resonator, and turn the receiving mirror about the line joining oscillator and resonator. During this operation, the resonator sparks become more and more feeble, and when the 2 focal lines are at right angles, as in Figure 31, no sparks whatever are obtained at the resonator, even when the 2 mirrors are moved up close to each other. In another method of showing that the electric waves are polarized, Hertz made use of a grating of wires. The wires of the grating were 1 millimeter in diameter and 3 centimeters apart, and were mounted in an octagonal wood frame 2 meters high and 2 meters long. When the grating was interposed between the oscillator and the resonator so that the direction of the wires of the grating was perpendicular to the oscillator and the resonator, as shown in position 1 in Figure 32, it allowed the sparks at the resonator to pass completely. With regard, then, to the transmission of energy, the screen behaves toward the electric waves as a tourmaline plate behaves toward a plain polarized ray of light. Another way of showing polarization of the electric waves was also devised by Hertz. The receiver was again placed so that its focal line was perpendicular to that of the oscillator, as in Figure 31. Under these circumstances, as already mentioned, no sparks appeared, nor were any sparks produced when the screen was interposed in the path of the waves, so long as the wires of the screen were either horizontal or vertical. But if the frame was set up in such a position that the wires were inclined at 45 degrees to the horizontal on either side, as Figure 33 shows, then the interposition of the screen immediately produced sparks at the resonator spark gap. Clearly, the screen resolves the electric force of the advancing wave into 2 components and transmits only that component which is perpendicular to the direction of its wires. This component is inclined at 45 degrees to the axis of the receiver, and so has a component along the direction of the resonator. From these experiments, it is evident that the interposition of the screen stops the waves when the wires of the screen are parallel to the electric component of the waves. It is in this position that the electric force would produce currents in the wires. The changing magnetic force at right angles to the wires would also produce currents in the wires, so that both the components, that is to say the whole electric wave, would be absorbed or reflected. Hertz showed that the action was one of reflection rather than of absorption. In this, the wire screen differs from the action of the tourmaline crystal on light, for the extinguished component in that case is absorbed rather than reflected. Refraction. Hertz also performed some experiments on the refraction of electric waves, employing for the purpose a large prism of pitch cast in a wooden box. The base of the prism was an isosceles triangle 1.2 meters on the side, and with a recting angle of nearly 30 degrees. The height of the prism was 1.5 meters, and its weight was 1,200 pounds. With the arrangement of apparatus as shown in figure 34, the rays were refracted by the prism through an angle of 22 degrees. From this value, Hertz calculated the index of refraction of the pitch to be 1.69, while the refractive index of pitch-like materials for light is given as being between 1.5 and 1.6. In concluding this series of experiments, Hertz says, "We have applied the term rays of electric force to the phenomena which we have investigated. We may perhaps further designate them as rays of light of very great wave length. The experiments described appear to me, at any rate, eminently adapted to remove any doubt as to the identity of light, radiant heat, and electromagnetic wave motion. I believe that from now on we shall have greater confidence in making use of the advantages which this identity enables us to derive both in the study of optics and of electricity." Experiments of Righi. Immediately following the discovery of electric waves by Hertz, a great number of experiments were made by various investigators in repetition of Hertz's experiments and in the effort to extend his results, particularly in the direction of the study of the properties of short electric waves, so as to obtain a further comparison of their properties with the properties of light. In order to obtain electric waves shorter than those of Hertz, Professor Righi of the University of Bologna devised an oscillator consisting of two spheres B and C, figure 35, separated by a small spark gap in oil. A and D are the terminals of an induction coil or electric machine used to charge the oscillator. These terminals are provided with the spheres A and D, which are separated from the spheres B and C of the oscillator by spark gaps in air, so that the oscillator BC is without metallic connection with the other parts of the circuit. The spheres B and C were fastened with shellac into the truncated cones of glass EF and GH, which were supported in an ebonite frame. The lower funnel-shaped glass vessel served to contain the oil. The spark length in oil between B and C could be regulated by the screw V. The advantage of having the spark between the spheres take place in oil instead of in air, as had already been pointed out by Saracen and de la Rive, arises from the fact that it takes a greater difference of potential to start a given length of spark and therefore gives a more energetic discharge. When the spark is once started, the oil is carbonized and becomes conducting, so that the succeeding oscillations pass with comparatively little damping. Also, the oil obviates the necessity of repeatedly polishing the terminals, as Hertz found he had to do when he attempted to get short waves with the spark in air. Righi found that Vaseline oil is especially well adapted for use with his oscillator. For a receiving apparatus, Righi made use of a resonator consisting of a strip of silver AB deposited on glass and interrupted by a diamond scratch C across the middle of the strip. This provided an extremely short spark gap between the two parts of the resonator, as shown in figure 36. Also, the spark across this small gap will occur more easily than a spark of equal length in free air. Righi's resonator is thus seen to be an extremely sensitive modification of the rectilinear resonator used by Hertz. In most of Righi's experiments, the oscillator and the resonator were mounted in cylindrical reflectors. The mounting of the resonator is shown in section in figure 37. The resonator is at A and is fastened upon a strip of ebonite BC. The observer looks through the converging lens at H, which serves to magnify the minute sparks between the two halves of the resonator. The apparatus could be used quantitatively by observing the angle through which it was necessary to turn the resonator and its reflector in the support LM in order to obliterate or minimize the sparks. The following table gives the dimensions of Righi's apparatus and the corresponding wavelengths obtained. For apparatus number 1, diameter of the spheres is 0.8 centimeters, length of resonator 0.9 centimeters, width 0.1 centimeter, giving a wavelength of 2.6 centimeters. For apparatus number 2, diameter of spheres 3.75 centimeters, resonator length 3.6 centimeters, width 0.2 centimeters, wavelength 10.6 centimeters. For apparatus number 3, diameter of spheres 8 centimeters, resonator length 10 centimeters, width 0.6 centimeters, wavelength 21.4 centimeters. In a test of the sensitiveness of various combinations of this apparatus, Righi found that with the resonator 3 and the oscillator 2, both armed with their respective cylindrical reflectors, sparks appeared across the minute diamond's grand scratch of the resonator when it was at a distance of 25 meters from the oscillator. This is a distance of 125 times the wavelength for this apparatus. With the oscillator 3, the sparks were evident at a greater distance. With resonator 2 and oscillator 2, the greatest distance to which indications of the waves could be obtained was 20 meters, which is 190 times the wavelength. While with the minute apparatus, resonator 1 and oscillator 1, the maximum distance was about 80 centimeters, which is 31 wavelengths. With this smaller apparatus, in spite of the comparative feebleness of the waves, many experiments that are commonly performed with light waves could be successfully carried out with the electric waves. For example, a small coin of 10 centimes could be used to reflect the waves. The coin does not need to be polished, as was with experiments on the reflection of light, because irregularities of the surface of the coin are too small to have any effect on the reflection of the electric waves. Refraction and total internal reflection of these short waves could be shown with prisms of sulfur or paraffin that were very little larger than the glass prisms used in optics. Righi also succeeded in demonstrating the double refraction and elliptic polarization of the waves by slabs of the wood of the fir tree. A thermal junction for measuring electric waves. Ignaz Klemenčič showed that a thermal junction could be employed to detect and measure the waves. Klemenčič's device, figure 38, consists of two thin sheets of brass MM, 10 centimeters broad and 30 centimeters long, placed 3 centimeters apart, and having soldered to them respectively a very fine platinum and a very fine platinum nickel wire, which were crossed at K and were thence conveyed off at right angles and soldered at their other ends to the leads L of a sensitive galvanometer. This resonating system was fixed at the focal line of a suitable cylindrical metallic reflector. When electric waves with the electric force parallel to MM fall on this receiver, electric oscillations between M and M produce heating of the knot K, which is the point of contact of two dissimilar metals, and in consequence the heat developed gives rise to a thermoelectromotive force at the knot, and consequently to a current in the galvanometer. By the use of this instrument and a Righi oscillator, Klemenčič has studied the reflection of electric waves from metals and insulators. Various investigators have made use of the Klemenčič thermal junction in quantitative experiments on electric waves. By reducing the size of the metal waves MM, Professor A.D. Cole has applied the apparatus to measurements with waves with a wavelength of 4 centimeters. Professor Lebedew, employing a slightly different form of thermal junction, worked with waves of wavelength of only 6 millimeters and succeeded in showing the double refraction of electric waves by crystals. A form of oscillator similar to that used by Cole and by Lebedew for producing their short electric waves is shown at 00, figure 39. Professor Lampa and Professor Bose have also succeeded in making measurements with electric waves of only 6 millimeters wavelength of electric waves and light. The following table contains in round numbers the value of wavelength and number of vibrations per second of some electric waves and waves of radiant heat and light. Commercial alternating current, wavelength 200 million centimeters, vibrations per second 150. Leyden jar discharge, wavelength 300,000 centimeters, vibrations per second 100,000. Hertz's first oscillator, wavelength 1,000 centimeters, vibrations per second 30 million. Hertz's rectilinear oscillator, wavelength 100 centimeters, vibrations per second 300 million. Righi's oscillator, wavelength 2.6 centimeters, vibrations per second 11,500,000,000. Lebedew and Bose's electric waves, wavelength 0.6 centimeters, vibrations per second 50 billion. Longest radiant heat, wavelength 0.1 centimeter, vibrations per second 300 billion. Orange-colored light, wavelength 6/100,000ths of a centimeter, vibrations per second 500 trillion. Shortest ultraviolet, Schumann, wavelength 1/10,000th of a centimeter, vibrations per second 3 quadrillion. Lyman, wavelength 100,000th of a centimeter, vibrations per second 30 quadrillion. Physicists have long been accustomed to recognize that the difference between radiant heat, visible light, and the actinic ultraviolet radiation is merely difference in wavelength, and that our greater familiarity with the visible portion of the spectrum arises merely from the fact that we have a particular set of nerves sensitive to these rays. The visible part of the spectrum lies between wavelengths 0.4 thousandths and 0.7 thousandths of a centimeter. By the aid of the thermopile and the photographic plate, the spectrum has been extended to include all the radiation with wavelength between 1/100,000th of a centimeter, extreme ultraviolet, and 1/10th of a centimeter, extreme infrared. This upper limit is about 100 times the lower limit. It is interesting to note that the Hertzian waves of Lebedeau, Lampa, and Bose have a wavelength close to this extreme wavelength of the limit attained in the infrared. That is to say, the shortest Hertzian waves that have been measured are nearer in wavelength to the longest measured heat waves than these are to the shortest measured ultraviolet. Also in properties, the Hertzian waves are nearer to the long heat radiations than these are to the ultraviolet or even to the visible. For example, some of the long heat waves, like the Hertzian waves, pass readily through vulcanite and other insulators opaque to visible light. Space is lacking to consider further the experimental evidence in favor of Maxwell's proposition that electric waves are of the same nature as light waves, and that the light waves are in fact simply electric waves of those particular wavelengths that possess the property of being capable of affecting the retinas of the eye.